Yeah, hello? Yeah, hello? Can you hear me? Yeah. Oh, you mean that after the session, how do you like propose the questions or something? Mm-hmm. Oh, that part, let me check my calendar because based on what I have know, there should be no gathering this. Let me check. Just a second. Mm. Yes, I think it's better to like propose your question during the session in the Zoom meeting. And in this case, I don't see any like extra time point for you to gather and discuss. Yeah. Sorry about that.
Hello.
Hi.
Can you see my slides?
Yeah, it's good.
See if I. Okay. Okay. Change the lighting a little. Okay. Good. Then I guess I will be muting a little until it starts.
Okay, thank you.
Oh, thank you.
Hi, Professor. Shall we start? Like, I have made you the co-host, and I will mute myself, and you can start the presentation. Is that fine? Hello, Professor. Can you hear me? Hello? Hi, Professor. So, can we
Hello.
start?
Yes, we can start.
I have made you the co-host, and you can start the presentation. I will mute myself.
Okay, and let me share my screen. Okay, then I hope you can all see my screen.
Yeah.
And you hear me, hopefully.
Yeah.
Okay, so I have some slides along about confidential computing. Whenever somebody has a question, please raise your hand or just ask me during that presentation. Or after, if you watch a recording, please send me an email. So there's for this lecture, there is some website where you can actually get exercises to this lecture. And let me give you just context. So what I present today is an introduction to confidential computing. So I will introduce some basics of confidential computing. So what is confidential computing? What do we use it for? So application domains. We'll focus a little bit on remote and local attestation. So what is this? Why do we need that? And introduce a set of problems in the context of confidential computing. And these problems I actually address in some later lectures. So today is really only introduction lecture where I raised some problems, but I do not address all these solutions to these problems. So this lecture is of course a part of a longer lecture series, so you would have to look at some later lectures. So I have some of the exercises at least online, so you can actually at the end of this lecture slides, you can actually look at, you get a link to the exercise session and you can actually do that yourself at home. Well, you have to register for getting access to the images. Anyhow, so this is kind of a context. So this is just the introduction to a larger lecture series. And let me start with confidential computing. So I want to start with a motivation. What is confidential computing? Where is it used? And as always, if you have questions, ask me. So confidential computing is mainly used these days in cloud computing. So we want to protect our application from the cloud provider typically, or the cloud wants to protect itself from applications. So they are dual use. So first protect the application, but also protect the cloud from applications. So there you can see the use of confidential computing. Research-wise, there's lots of activities in the edge cloud. So having computation closer to the applications. And there we have the interesting problem that we have less physical security, and how can we actually protect our application if there is little physical security. So therefore, edge cloud is a very interesting application domain for confidential computing. Any questions? I hear somebody. Then there's also air-gapped systems. So you have sometimes manufacturing halls where there is no internet connectivity, and still you have to provide some applications that are protected. And there, confidential computing is actually also used, and there you have some extra problems that we need to address. And I, at least in this first lecture, I raised some of these problems. This is context embedded systems. There is also use for confidential computing in embedded systems. Here again, limited connectivity. Some, yes, questions? Anyhow?
No.
Okay. So you have limited connectivity, limited physical security in some of the embedded systems, and their confidential computing might also help you. In Germany, where I'm from, there we have the requirement of using confidential computing for e-health. So electronic health records are need to be protected by confidential computing, meaning that they all need to be encrypted. Is that an interesting domain, confidential computing? If you look at the expected market share of confidential computing, so this is expected to grow over the next years, so from maybe $2 billion in 2021 to more than $50 billion in 2026, at least according to some analysts. So there is some development, commercial development in confidential computing domain. So there's also lots of innovation right now. So therefore, this is an interesting domain, both from commercial perspective as well as academic perspective. And so now let's look at some motivation why we would like to have confidential computing. And here I have a very abstract view of a data center. And there we have some CPUs, some servers, there might be some BIOS, we have hypervisors, virtual machine, operating system, applications. And this is really complex these days to manage this computing infrastructure. So therefore, cloud computing has taken off over the last decade. So there are more and more usage of cloud computing where you outsource that management of the of your computing infrastructure to somebody else, like Amazon or Microsoft. And therefore, they have expertise to run that infrastructure. And if you look at the total cost of ownership, that might actually be cheaper than running it yourself, because you have to hire people to have expertise in all these technologies. And so what we want to have is that we as an application owner, and I always take the view of the application owner, I want to protect my application, and I want to outsource the management of all that infrastructure. So I want to use the infrastructure of some provider, typically a cloud provider. And that cloud provider wants to protect his or her infrastructure. So the focus is on protecting the infrastructure from the application owner. While when I take the role of the application owner, I want to protect my application from the infrastructure owner of the provider. So there is some conflict, potential conflict, so different interests. So we have different stakeholders, and we need to solve that. So traditionally, if I manage my own infrastructure, there was less of that conflict, because all the management was done by the same company, so they all had aligned goals. Now it might be different, that we outsource the administration or management of the infrastructure. And what we want to do these days is even that we outsource the management of the application itself. So I go to some provider, and that provider should manage my application. So that means I, as an application owner, I would like to keep control over my data, my code, my secrets. But at the same time, I want to outsource the management. So this seems to be impossible to do. And what we aim in confidential computing is that we enable application owners, so some stakeholder that wants to provide some service or owns the data or the code, and that wants to make money with his or her service, but doesn't want to manage the infrastructure. So in their confidential app computation might help. And so there, I would like to zoom into that problem during that slide deck of today. And so let me try to kind of look at system security, because that is a more established domain. So in system security, we protect the infrastructure from adversaries. Also, typically from applications, because in system security, we consider the application owner as a potential adversary that tries to use her or his application to attack the system. And so therefore, in system security, we try to protect the infrastructure from the application. And typically, we have a layered infrastructure. So we have on the bottom, we might have a hypervisor. The hypervisor is trusted by the operating system that runs inside the virtual machine, but the hypervisor doesn't trust the virtual machine because that might be under control of some other entity, some other stakeholder. Inside the VM, there might be container engine that might not be trusted by the OS, but the container engine has to trust the OS. And there might be Kubernetes on top, and it might need to trust the operating system underneath. So that means typically we have a layered infrastructure, and the layer I+1 is not trusted by layer I, but layer I+1 needs to trust the layer underneath. And so that means the application is typically not trusted. What we want to do in confidential computing is to focus on the application, because that is what most users, application owners, I should say, want to protect. I have a certain application, I want to run that in the cloud, and I care less about the infrastructure. I care mainly about my application. Of course, if the infrastructure is very secure, I also appreciate that, because that protects also my application. And so therefore, as an application owner, as a stakeholder, that application owner, I want to protect my application. My application consists of, abstractly at least, of code. So my programs, my data, address that I store on disk, and secrets, key material that I might need to encrypt or decrypt data. And I want to protect that from adversaries that want to steal my data. There's a question, please go for it.
Sir, here we are talking about the running our application at the cloud, like cloud will manage our application. Will the same thing will apply if we think of a embedded system running a application?
Yes.
I think management will be on us, and in this case, management is on the cloud side. But the point which we are focusing on that is code, data, and secret. The same principles will apply both the sides.
So in my opinion, the embedded world will also change. So you will have these edge clouds, you will have more centralized infrastructure, at least if you go to production environments. And there you will have also the problem that you have less and less of your own hardware and more hardware that is shared. So you might outsource some of your computation needs to some cloud computing close by. And you might say, okay, that is too far away, but I would say that is not that far away, that because these days you have more and more computational needs. If you're in embedded domain, you want to reduce kind of the energy, the cost of your device, and you will see that you also move some of the computation in more centralized environments close by, which you would call now edge clouds. Does this make sense?
Yes, sir.
Oh. Okay, cool. Okay. So that means, and then maybe I should have emphasized that initially more. So this is the edge cloud, I think, is important for also embedded domain. And also for embedded domain, you have less physical protection. Their confidential computing will take off also in a few years, because now with ARM also supporting confidential computing, there will be more usage of that in the embedded domain. Okay, so what I want to do is protect my application. And I want to protect the confidentiality, the integrity, and the consistency. So what does this mean? Confidentiality means that only authorized users, or entities, I should say, can see the information. So and the information might be data, code, secrets. So I might want to protect confidentiality not only of my data, but also code. Say I have Python code that does some interesting machine learning, and I want to protect that code so that no competitor can actually copy my code. I also have secrets to encrypt that data, so I want to protect these, of course, because otherwise adversaries can decrypt my data. There is also integrity, so that means only authorized entities are permitted to modify the information, so that means code, data, and secrets. And all the unauthorized entities, at least when they modify it, we want to detect that the code, data, or secrets were modified. For example, secrets modification would be that they give us now an old secret that it was already is already known to the adversary. And consistency is slightly ambiguous term, let's put it this way. In consistency means that we always read the latest information, so the latest data, code, and secrets. But that was written by an authorized entity. So that means nobody can give me old data that doesn't reflect all the updates that we have seen, or like old code that has known vulnerabilities. So I should always go for the newest code. Okay, so there is consistency. integrity and confidentiality that we all want to protect against, or want to protect against adversaries. And here, the adversary might be external hacker, but it might also be the cloud provider. So we have requirements, for example, in the electronic health domain, that cloud provider must not be able to look into my application. The cloud provider can operate the infrastructure, can manage the infrastructure, but it must not be able to access the application. Okay, so we need to protect our application. And the idea is that we have something like that is called a confidential computing environment, kind of a box where our application runs in. We protect everything in there, and we keep the adversary and the provider, cloud provider, outside. Of course, that is not that easy as just drawing a box around. So we have to address a sequence of problems to make that vision true, that we can protect our application from the cloud provider and very powerful adversaries. So in my mind, there is a complementary of system security and confidential computing. Not everybody might agree with that, but if for my application-oriented view, I would like to run in the most secure environment. So that means that the infrastructure provider, cloud provider, protects the environment as well as possible. Because there might be adversaries that try to attack the infrastructure to get to my applications. The better the infrastructure is protected, so the better my cloud provider is, the less chances the adversary will have to get to my application. I also want to make sure that other applications that might break out of their sandboxes, so that run on that same cloud infrastructure, if they break out, they should not have a chance to get to my application. So therefore, system security is most important to make sure that my application is well protected. But system security does not protect it against access from the cloud provider, from the infrastructure provider. So therefore, we need more than system security. We also need confidential computing for protecting our application. Something that confidential computing does not ensure is availability. Availability is the probability that our system, application, or service is available at a certain point in time. And typically, we do that in nines. We give that availability in 4 nines, means 99.99%. 6 nines will be 99.9999%. So there, confidential computing does not help you with respect to availability. So this is not a goal of confidential computing. What you typically do is you run your application in some environment where you can use standard fault tolerance mechanisms to improve the availability. Like if you run on Kubernetes, you would restart your application, or Kubernetes restarts your application. In case there's a crash, it restarts on the same node. If the node was crashed, it restarts it on a different node. So there are some really nice mechanisms in production that you can use. And this is complementary to confidential computing. And what you typically would do is you have a service level agreement with your cloud provider that manages your application, where you say, okay, I need 6 nines. And then if the cloud provider is not able to do so, you have some agreement that the cloud provider pays a penalty. So there you have SLAs with your provider, and that most of the time is good enough. Confidentiality, you might ask yourself, why don't we do the same thing? Because it's really difficult to see if there was some leakage of data. If that is done in a good manner, or in a if that adversary is powerful, it can just copy your data and you might not even know it. So from that perspective, availability is not a focus of confidential computing, because typically it's assumed we have used some additional complementary mechanisms there. Durability is also not the focus of confidential computing. So durability is the probability that some data item will be accessible after 1 year. So typically you want to have durability of your persistent data of 11 nines or something like that. So lots of nines, so that you have a very small likelihood that your data is lost. Okay. If you have any questions, just raise your hand, try to look if somebody has questions and then try to address that. Okay, so let's look at the first problem, or problem 0. In the definition of confidential computing, or I should say of confidentiality, integrity, consistency, I was talking about authorized users or entities. One question is, if my hypervisor operating system is managed by somebody I don't trust, how do I know what or who is authorized? So this is the first question that you should ask yourself. How do we know who's authorized and not? Because that determines who can see the data. And typically the operating system defines access control. And there, if you cannot trust the operating system anymore, things get suddenly blurry or difficult. So therefore, something that to keep in mind is authorization is getting not as simple as we typically think of authorization, because we typically have users in the operating system, and that determines the user has certain roles, and that with role-based access control, we define who has access to certain data items. So in confidential computing, we somehow need to define who is okay to access certain data, code, or secrets. So in data code and secrets could be persistent, so on disk. Typically, we have some role-based access model in systems like Kubernetes. And if we don't trust that anymore, so how can we know that somebody has access? Also in flight, so we communicate with each other. So how do I know that my entity that I communicate with is authorized to receive the data or send me the data? And also in use, so in memory, how can I make sure who's authorized to access certain code or piece of data? Okay. That was the wrong direction. Availability and durability, I mentioned already, is not the focus here. There we assume somebody else takes care of. Let me give you an example. So typically I have to store data. Then I have to store the data, and then I might want to perform some learning. So I use the data to train some AI models. For that, I need code that actually helps me to create that model. And so often these days, these are written in Python. And so I have Python code that needs to be protected. If I put lots of energy in my Python codes, lots of resources, and then I don't want my competitors just to copy that code. So I have to protect that Python code. I also have to protect the data. And of course, I have to protect the secrets that I use to, say, encrypt my data. And one example how I could do that, I have a database. You might use SQLite in embedded domain. You might use MariaDB in a little bit more powerful servers. And these databases, they support SQL, and they support encryption of the database. And when you look at MariaDB, it supports an encryption key that is stored in a configuration file. And that configuration file is somewhere in /etc/mariadb.conf or my.conf. So you have a certain configuration file, and there the configuration of MariaDB is stored, in particular the encryption key. And the access to that file is controlled via access control of your file system. So you say that only the MariaDB user can access that file, but no other user. But if I'm the adversary and I have root access on your machine, I can just read that file. I don't care about this access control. Worst case, I change the access control as a root user and read the file, configuration file from MariaDB, and I can then read the data, decrypt the data, whatever is in there. It is not protected from me as a root user. So therefore, the question is it sufficient to have kind of authorization being defined by the operating system? So any operating system defines access control and defines who's the user. But if I'm an admin and it become any user that I want, I have access to any data and any secret. And you might say, well, that is how things are. But if you look in domains like electronic health records, you must exclude admins from being able to read data. Or if you're in a company, you have to make sure that your admin cannot read the emails of the management, for example. So you have to have a limit of what a root user can do on a system. So cannot read the data, cannot read the encryption key for your emails. So there are kind of protection that you need and limit the impact of root users. So therefore, we have to make sure, or by doing that, when we have an adversary, typically what they do is they become root users to gain access to the data. Or the other thing that we have is that users might have access to certain data and then they are getting laid off, or they go to another company and then they copy the data before they join the other company or their startup. So we have to make sure that we limit access to confidential data. And so therefore we have to have a appropriate threat model, how that defines what kind of adversaries do we expect. And there's always the difficulty, what kind of threat model is realistic. It often depends on my application. If there's not too valuable data in my application, maybe I don't have to protect it too much. But if there's lots of money involved, so if somebody could get the data or the keys of my applications and make lots of money, maybe I should have more strict or more explicit threat model, because adversaries might go the extra mile to get to my data. And then when you then start reading about it, then you see all kinds of papers. There are tons of papers that look at attacks on your application. I mentioned here only before the root user. So when I'm an admin, I can access everything. There are more advanced attacks where I can roll back time to access kind of old states of the system. In embedded domain, this is one of the difficulties. Say I have really old software, and so typically as an adversary, I have a real easy time because I know all the vulnerabilities in the system. I just attack the system by using the known vulnerabilities and get access. So there I have an interesting problem that I can address it to some extent with confidential computing. There's insider attacks, Sybil attacks. Sybil attacks is I just imitate the existing system. There are side channels where which are very popular over the last few years, where I try to use, for example, caching behavior or look at my cache to derive some secrets. I can also do physical attacks on my system to learn about application systems. There's, for example, Plunder Vault that lowers the voltage of the CPU and then cause some miscomputation where it maybe sometimes some secrets are exposed to the adversary or the integrity is violated. So what we do in our research and our work, we use a certain threat model, actually one from Intel. There are, in the Intel model, there are 9 kind of levels, adversaries that one looks at. We add some more level, the rollback state adversary. But you can follow that link that is on the bottom of the slide, and there you see a certain set of adversaries that you might want to consider in your systems when you want to protect against adversaries. And I will only talk about the first one, unprivileged software adversary and system software adversary today. So if I'm in a cloud environment, as an adversary, it's nice. I can just go to Amazon, Microsoft. If your application runs there, I could try to run my attack application on this cloud. Of course, that is much, much more difficult than just running an application on the cloud, because typically there are thousands or 100,000s of machines, and it's very unlikely that my application gets scheduled on the same machine as yours. There might be also, there's a very good isolation between the different applications. There is also, if I'm a defender, so if I'm having an application, I might also use bare metal server where no other application runs on the same machines, on the same machines that I use. And so from that perspective, having unprivileged programs on the same cloud is really difficult for an application, for an adversary to actually attack the defender's application, so the application owner's application. But the defender has also problems to protect its application. So how does the defender know that there is no other application running on the same host? So there are all kinds of interesting problems that we need to address. But the assumption here, so instead of deep diving in there, so the assumption is typically that we assume that there's some other application running on the same machine as we have, and we need to defend ourselves against that. The more interesting part is that, and that you don't typically have in traditional systems, also embedded systems, is that we have a system software adversary. We assume that the admin or the adversary has admin credentials and can use the system to the, like an admin, can modify the system software, might copy data arbitrarily in the system, might even change the operating system to fit his or her needs. And if you look at most operating system, if I'm admin, I can dump the memory of the system. So any software that you have in Python, I can copy any keys that you have. Is typically must be in the main memory, so I can copy that key that you have from main memory, extract it from your main memory, and I get access to it if I'm the adversary with system access. That is kind of the focus of confidential computing, that we protect against adversaries that have root access. And the motivation again is that we outsource the management of the system. Somebody takes care of it. In the embedded domain, we use some edge cloud that is managed by somebody, and we want to run some code in that edge cloud to make to offload some computation. And now we have the problem that we cannot necessarily trust that edge cloud. So therefore, we typically assume that adversary has root access. There might be multiple reasons for that. I mentioned already a few. Let me skip the rest of these. And so the main problem here is, how can I ensure confidentiality, integrity, and consistency if the adversary has root access? So and that's what I would like to address in the remainder of the slide deck. What I don't address in my slide deck is how can we actually outsource the management of my application to somebody I don't trust. So I'm the application owner. I have this great application. I don't have the staff to manage that. So I give the management to somebody else that I do not trust. This provider might want to look at my data, but I want to give the management of my application to that entity to take care of my application. But I don't trust it, and I want to make sure that this adversary that manages my application doesn't get to my data. So this is an interesting problem that you can actually solve with confidential computing, but I have not the time to actually address this in today's lecture. There are some more advanced lectures where I look at this problem. Another interesting problem that I do not address in this lecture. Yes, please. Question? No. Okay. Is air-gapped. So I have some computation in some, say, production floor, manufacturing floor, and I don't have internet connection, and I cannot do certain external checking. And so how can I protect confidentiality, integrity, and consistency when I'm completely air-gapped? And so there's some interesting problems and solutions how we can use confidential computing to actually support air-gapped applications. Okay, so, but this is not, there's not enough time to look at all of these problems. So I give you just a top-level introduction how to address the first problem. And typically what we do is we have different application types and deployment types. These days, if you have embedded domain, you might be on bare metal, but my expectation is you go also in the embedded domain more and more towards container deployment. You might even have VMs. In the cloud, we have containers inside of VMs. That is the standard today. So we run Kubernetes, which is the default orchestrator. These days, you run a container in a VM. And in a few years, you actually go that you have containers that use hardware isolation mainly, so these Kata containers. So you run a VM for each container that runs itself in a VM. So you have these nested VMs, and so you have quite some complexity that you have these days. Anyhow, so confidential computing you can use on all levels, whatever your deployment level is. If you want to use bare metal or you want to have the Kata container inside of VMs, you can use it in different deployment types. And embedded, you might have most of them, I would call it command line interface. You have a simple application running, but you can also run Docker containers. So Docker containers become more and more popular because it's just easier to deploy applications. These days, you see maybe in we see in the embedded domain that people start using Docker Compose to run the application using containers because that's easier to deploy. And in the cloud domain, you use actually many containers spread across multiple machines, and there you use Kubernetes to orchestrate that, at least today. Future, there might be something else, but right now this is the de facto orchestrator that people are using. Maybe in a few years, you might use that in the edge cloud for offloading application components. And there you might also use what is called cloud native application. So I have a little introduction to cloud native application because I think this is a really nice way to build your application, even for embedded systems. You want to structure your application such that you have services that talk to each other. This allows you to divide and conquer with respect to your development team. Each service can be implemented by individual team of developers. They have their different skills. They might use different application or languages. They might use different frameworks that they know, and then you connect all these applications to services together into one big application. And these days, you take your service microservice instance and you deploy that with containers, and then sometimes these are called containerized services. And these services you create a container image, and then that container image is like a root file system that is copied to some of the machines, and then it's started. This has great advantages because you get rid, or you address all this dependency hell that you have, in the sense that typically you have always problems that you need different libraries, and for one application's instance or for one service, and you need other libraries for other services, and that you can control by having these containers. And cloud native is really great way to develop application, because you support these different application programming languages. You have to drink some, sorry. You can solve most of the scaling of the application. You can have standard service that you integrate. So there are lots of interesting advantages. Of course, there are also disadvantages that it's not easy to understand all the complexity of cloud native applications. So the Kubernetes, you have a really steep learning curve if you haven't used that. So there you get lots of advantages, but only if you learned all your lessons about Kubernetes. Kubernetes, you have containers. As I mentioned, this is not necessary for confidential computing. Many companies actually use, or some of the companies, they don't use Kubernetes, they just use containers or deploy bare metal without containers on the machines. But here, this is something that a cloud native application might look like. So you have some application service in the middle. You might have some proxy that communicates with clients. You might use some caching to speed up your computation. You might have some persistent data that you have an embedded database like SQLite. So you have a set of services that talk to each other. And if you look at smartphones, so these days on the smartphone, you might have SQLite there. You might have your application service running in Python, and you might use some local caching to do some speed up of your application. And so I think this is a common pattern that you see in applications. And what you have seen over the last decade is that you see more and more applications that use REST APIs. So that means you have an application service that's focused on a single aspect, so single functionality that's implemented by that service. You have just one developer team that drives this application service, and in this way you develop your application faster because you remove the dependency between the different components of your application by having a well-defined application or service API, and that API hopefully stays pretty constant, and then the different teams can just talk to each other via the REST API. And the REST API, just as a reminder, it stands for representational state transfer. So we have kind of a HTTP methods to talk to the application. So we can create some resource, we can retrieve some resource with a GET, we can update a resource or delete a resource. So we have a fixed number of methods, which is different from RPC, remote procedure call, in the old ways, because there you had kind of different methods, always different kind of methods. Here now we have fixed set of methods, CRUD, so create, retrieve, update, and delete. But we have lots of resources now. Anyhow, when you then build your applications these days, you have multiple instances of your services here on you have IP 1, 2, 3, so that each instance gets typically an individual IP address. And then when a client wants to talk to the service, you have a load balancer that's addressed via some service name. The client just says, okay, I want to talk, send a request to that service, use the name, gets forward to the load balancer, and the load balancer forwards the request to one of the application instances. Okay, so this is just a little intro or a reminder how things are working in cloud native. And the focus of this lecture is on cloud confidential applications. So what you want to do is that you build your application for any of the deployments that we've seen. And we want to make sure that our adversary that has root access cannot get to our application. Administrator after cloud or Kubernetes or any administrator should not be able to get to our application. So that means we would like to have a box around our application. And typically our application is sandbox, so it cannot get out of its sandbox. But here what we want to make sure it's kind of the opposite, so that the outsider cannot go into that box. And that is called a trusted execution environment. So we want to make sure that all the adversaries stay out and only the application components can talk to each other. And so that we kind of have an environment, a trusted execution environment where our services can run and where they are protected from the adversaries. And so what you typically do is you make sure that all the service components, service instance, like the proxy, here the service that performs the application functionality, the cache, the database, they are all protected when they are in use, so while in memory. You also want to make sure that all the communication between them is protected. And there you typically use something that is called MTLS, mutual TLS, where you authenticate, you make sure you authenticate the client in the service. So you make sure that the service only talks to known clients, like the service might only accept requests from the proxy. And the proxy needs to make sure that it talks to the right service of the same application. And so with MTLS, you make sure that you only two entities that belong to the same application talk to each other. And you also want to make sure that data at rest, so the things on disk, are encrypted. And you have to encrypt it in such a way that it's not accessible by the admin. So it must not only be encrypted by Kubernetes, it must not only be encrypted by the operating system. You want to make sure that it is encrypted in such a way that only the application can access that data at rest. Okay, so this is kind of what we want to ensure with confidential computing. And coming back to embedded domain, so this is right now kind of possible using Intel CPUs, AMD CPUs, and soon by ARM CPUs, which are more used in embedded domain. Okay. So then, when we encrypt all that, so when we encrypt the data at rest, the communication between the services, how can we manage the keys, the secrets that are used to encrypt the data in transit or at rest? So at rest, we typically use symmetric keys, while for MTLS, we use asymmetric keys, so public-private key pairs. And so we have that problem, how to manage that so that only our application gets access to the keys, but not the adversary. Okay. So let's focus a little bit on the protection in use. So at runtime, when our service is running in memory, and when my service runs in memory, say in Linux or Windows, then if I'm an admin, I typically can get a copy of all the data that is in main memory. So there's a dev-mem device that I might be able to use to get access to all the data that is in main memory via root access. And that we need to prevent, because the admin should not get to the secrets of our confidential service or application. And so what you have these days is you have CPU extensions that allow me to put my code data in main memory such that only my service can access this. This is encrypted memory regions are supported. These are called enclaves. There are different kinds of enclaves. There are some it's only parts of application, some process, some they are whole virtual machines. So there are different hardware implementation for that. And I get back to that point in a sec. And the idea is that only the code in the enclave can actually access the data, code, and secrets that are in that encrypted memory region. And every application that is on the outside cannot see that data at all, or this memory region, or if it would see it, it would only see encrypted memory. So that means if you have hardware access, like seeing all the memory traffic to the DRAM, you would only see encrypted data. We have, in my group, we have developed one platform that's called SCON, which stands for Secure Container Environment, which is one of the confidential computing platforms. And some of the examples that I have here in the slides are, you can see also on scondocs.github.com. So there's some more documentation. There's also some more slides and tutorials if you want to try this out. Okay. And this encrypted memory region is often called a trusted execution environment. So, and that is in most cases implemented with the CPU extensions. There are different ways how you could implement trusted execution environments, but these days there's some extension to our instruction set. And then you can create such encrypted memory regions, which, so the enclave. And most of the time you use a random key. So if I create an enclave, then a random key is generated by the CPU, and nobody can access that memory region except the code that runs inside of the enclave. But you have to be careful. So there are some enclave technologies where I can set that key externally. That means if that key is set externally, I have to be careful that to protect that key so that nobody else can actually access my data. So there is some problem if you have an externally given key that you have to protect that. It helps typically, or why do we have that? It helps to migrate that data. So one could, if somebody knows that key, how you encrypt that memory region, you could migrate that enclave from one server or one CPU to another, and then can continue executing on different CPU. So there's some trade-offs, so you have to be a little careful. And there are different granularities of how large this memory region is. So one of the early TEs is Intel SGX. There is parts of a process, and then the newer machines they use like SCV, SNP from AMD, or realms from ARM, or Intel TDX, they encrypt virtual machines, which in my opinion might not be a perfect fit for container-based workloads. There you might have a little too large granularity. So most of the time when I want to outsource the management of the Kubernetes cluster there, I would like to only protect certain applications. And then spending a whole VM to protect just a single process might be not super resource efficient. Okay. So let me deep dive a little bit into Intel SGX. Oh, there's a question. Please go for it. Praveen?
Sir, for the ARM platform, we have ARM Trust Zone, and there is some M series for the ARM where they provide this separating the hardware for security purpose. Like they will provide one trusted execution environment. So will that, can you say something on that part?
So not sure that I completely understand your question. So there is trust zone on ARMs already. So this is kind of a different isolation level in my mind for kind of a trusted OS versus an untrusted OS, but there you don't have encrypted memory. But the new ARM extension, the realms, which hopefully hardware will be available soon, there you can have encrypted VMs like similar to what you have from AMD SEV. So you define your encrypted VMs. There you can have your protect all the secrets, and there the code you can protect in that encrypted VM. And the advantage of realms versus trust zone is that in trust zone you had only one trusted zone. With realms you will have multiple encrypted VMs, and so you can have multiple different application that you can protect with realms. I'm not sure if that is.
Yes, I got it. Yes.
Okay, cool. Any follow-up? No. Then, so here the Intel SGX was one of the earlier introduction of trusted execution environments. So they announced it 2014, and that's also when my group started to look at this with the specification before the hardware was available in 2015. So right now, focus of Intel seems to be on server CPUs. So in the Ice Lake servers, you can have a 0.5 terabyte of encrypted memory. There are more server CPUs coming out. So there's Sapphire Rapids. If you look on Wikipedia, it also has SGX, and it's coming out end of this year or start of next year. I don't know. So there are server CPUs that support SGX. Initially, there was also laptops and desktops, but the focus these days of SGX is on server CPUs. And there, the idea is that you can use the SGX to protect the application from the infrastructure owner, the platform owner. Whoever owns that computer cannot access the data that it runs inside of these enclaves. And there, one can have different views if that is good or not. So some people might not see that as a good feature because you could protect some data that's in there. I would say my opinion is I want to run applications somewhere, not on my computer, but somebody else's computer. Then, of course, these enclaves are great because I can run in an encrypted memory region. I only have to trust the CPU chip and my code that runs in the enclave, and then I can protect my intellectual property. And there is then the interesting question. So how can I establish trust in the CPU, in the code that runs in the enclave? So how do I know that that CPU is a real CPU that I run on? It could be also an emulated CPU by QEMU or some other emulators. So it runs in software, and then whoever controls that emulator could look at all my secrets. So how do I know that this is real hardware, real trusted execution environment? And how do I know that this is not old hardware with known vulnerabilities? And also, how do I know that my code runs in that enclave? So when I give it secrets there, I want to make sure that these secrets, my encryption keys, are protected. And this problem will be addressed by attestation and verification, which is an important part, I would say, one of the most important parts of confidential computing. Okay. So SGX, Intel SGX introduced the notion of enclave, so encrypted memory region. They have some extra hardware on the chip that does the encryption. So they have a memory encryption engine that makes sure that there's no plain text in the main memory. So everything that is written to main memory is encrypted, at least in the region of the enclaves. And when then read on the CPU, it is decrypted and sits in plain text in the cache lines. So therefore, it's also important that the CPU protects access to these cache lines. Only the code in the enclave, running in the enclave, can see the unencrypted data. All the other code will not be able to access these cache lines that contain the unencrypted plain text data. And so even privileged code like OS hypervisor cannot get to the plain text data and code of the enclaves. And this is one way now where we can protect applications. So in the old way, always the operating system could protect itself from the application. Now with these CPU extensions, we can protect the application from the infrastructure. And that is important in cloud computing. Again, we run on an infrastructure that is not owned by us. It's not in control. We are not controlling that. So there might be a stakeholder that might copy our data and code. And this allows us to protect our data in code. So the important part is we can make sure that nobody else can access our code data and secrets as long as it stays in this encrypted memory region. And our code that runs in the enclave can actually access to the outside. So we have to make sure that we don't store all our data on the outside of the enclave. That is always a worry if you have programs running in the enclave. But if you are careful, then you have a decent or good protection of your code data and secrets. Okay, so this is good. This allows us to protect our applications. If you look in the research of confidential computing, so there have been quite a few papers over the last decade, well, not decade, but say 8 years. And there, some of the focus was on how should we architect these confidential computing environments. And there are different approaches, and so I will zoom into some of them. And something that is done in SGX is we have to make sure that when we enter an enclave, that we only enter at certain entry points. Because if you could just jump into an enclave at an arbitrary point, I could, as an adversary, could check which sequence of codes or can I use to exploit some secrets. So I have to, as a defender, so as the owner of the code that runs in such a trusted component, I need to make sure that only certain functions can be called with certain input data, and I validate all the input data. I only let certain function calls be performed, and then in this way I can kind of do access control to my enclave. And in Intel speak, that these are e-calls. So when I want to enter enclave, I can do that via certain syscall. I enter it via edge routine, and then I can perform some code. Sometimes the code that runs inside of the enclave needs to call some external code. This is called an O-call. So I call some outside function in there. I need to tell the CPU, now I want to leave the enclave. So I cannot just jump outside, because that would be too dangerous to just call. Yeah, I call a function, suddenly I'm on the outside. So I have to explicitly say when I want to have my control for going to the outside. One of the problem here is that the E-calls and O-calls are very expensive. So these are, because they flush the L1 and L2 cache, they take thousands of CPU cycles, so it's actually pretty slow. So what we did in OSDI 2016, so my group, we submit papers going there. We, instead of exiting the enclave, we keep the threads inside of the enclave. We use a shared memory queue and perform kind of like a remote procedure calls that actually gives us a higher throughput. The runtime from Intel, which is called Grameen these days, calls it exitless system calls. So there one can look at the advantages and disadvantages of E calls versus kind of exitless system calls. And in our observation here, if you have high throughput system servers that have lots of system calls, because typically we do the E call or the O call, I should say, for a system call, their shared memory queue is really good when you have high number of system calls per second, so high frequency. If you have only low frequency there, you have a higher CPU usage, and therefore you might want to exit. You might want to use O calls for system calls. So it's going, you can decide as an application what you want to use, if you want to do exitless or if you want to use O calls for system calls, and you optimize that. And typically, if you have high throughput, you use the asynchronous call, which we, or the exitless system calls, and otherwise you use the O calls. So there are some optimizations that one can do. The other thing that we have been looking at on the research side is how to partition applications, because Intel said, or take your application, cut it in parts that need to be trusted, some that are not trusted. This resulted actually in the observation that it's really difficult to protect the interface between confidential and non-confidential. Something that we do already in cloud native is that we have APIs that are externalized. So we have REST APIs. And that in our experience is good. So you define in cloud native just which service needs to be confidential and which are not. And you make these that should be confidential, you run them in enclaves. And those who are not, don't need to be confidential because they don't have any interesting data, or they don't have any secrets that need to be protected, or code that needs to be protected. You run them natively. Okay. So therefore, our approach is typically use microservices and then decide per microservice if that should be confidential or not. Okay, so let me zoom into some more technical details. So what you see here is different architectures that you see in practice. On the left side, it's an architecture of Grameen. So this is now the system architecture of enclaves. You could run in your enclave your own operating system to make sure that everything that your application does is protected. So you have your own operating system along with your application code. You could also say every system call, every shim, libc call is actually forward to the outside. There are also some application or some runtimes that do it in this way. Or what in our runtime we have the C library inside, and we have what's called a shielding layer on the bottom, but you also see in the library OS case. So the question that you face, so should we put in our enclave OS or not? And that was one of the research questions that we addressed in our research. And we decided on the right side for kind of having a C library in the enclave, but no operating system. And the reason for that was that we want to have better Kubernetes integration. So we don't want to, I guess there's some slide missing here. So one goal was to have a better Kubernetes integration. So we don't want to have our operating system, extra operating system. We want to just use the operating system from our cloud orchestrator. And therefore, one of the design decision was that we don't want to have a library OS in there because the integration would be easier in some sense. So if you look at Kubernetes, how it works, so I'm not sure how many of you have looked at Kubernetes. So there you have nodes, a set of nodes. Each node is typically VM or bare metal machine, and there you run your operating system. The operating system gives access to disks, which are called here volumes, and networking is done via something that's called kubeproxy, and your containers, they run in something that's called pods. And so what you have to do to support confidential computing is to kind of your service that runs inside of such a container inside of an enclave, it should look like a normal application to the Kubernetes infrastructure to make sure that you don't have to change Kubernetes. And to the application, you want to make sure it looks like it runs in a Kubernetes cluster, but you want to transparently protect all the data that you write out. You want to encrypt stuff that you write on disk. you want to make sure that you can encrypt network traffic transparently for the application, but you also want to make sure that you can use the connectivity of your Kubernetes node. So there are lots of technical details that one needs to address that to the application. It seems to be transparently running in a Kubernetes cluster. For Kubernetes, it should look like the application is transparent, or is a normal native Kubernetes application, but in reality, everything is encrypted. That is kind of the objective that we are aiming at. So it looks all like native computation, but in reality, you have encryption of all the data and code and network traffic of the services that run in your Kubernetes cluster. And so, so therefore, we looked at the two alternatives. We actually implemented with a group, with multiple other research groups, actually two alternatives. One where we used Linux kernel inside of Enclave, and the other where we only used the C library inside of the Enclave. And from a performance perspective, this right solution that you see on the slide was more performant and was easy to integrate with Kubernetes. In some of that performance measurements, you can actually look up in the OSI 2016 paper. So it's a little age now, but it's still valid, so that the right-hand side gives us better performance than the left-hand side. Okay. Another thing that from an architecture perspective is, how do I structure my application? I mentioned before already that we structure in microservices. And here's how you actually envisioned originally enclaves. So you have your application, and there you have application code, and there you have some parts of your application code should be an enclave. That part that has to process the most sensitive data. And that enclave can then have multiple threads, and it protects all the code and the data that's inside of that encrypted memory region. We tried that. We actually tried to build tools to take parts of the application, move it into such an enclave. And it was really, really difficult to build tools that protect parts of your application, because you have to have lots of knowledge how to protect that API. And it was, in our experiments, in our approach that we investigated, really difficult to automate this partition of the application in sensitive and non-sensitive code. So therefore, we decided, at least for my group, we decided that it is better to kind of take the help of the application developer, in the sense that the application developer anyhow partitions application into microservices, and then decide on a microservice case what should be in the confidential and what should not be confidential. So therefore, we decided for application model where the whole user process is inside of our enclave, except for some starter code that starts the application, so that takes the application code and some data, puts it in an enclave and starts it then. And for the application code that runs in the enclave, it looks like a native application. I mentioned already for Kubernetes, it looks like that application is native, but in reality, all the code and data inside of that user process is protected by encrypted memory, by enclave. Okay. So far so good. So we can, when such a, we call it sconified application starts, it starts inside of an enclave. But if you look at the details of Intel SGX, if I'm root, I see all the code, all the data that's put in such an enclave. So that means everything that is in this encrypted memory region in the beginning is known. So because during the copying, root can actually see all the initial state of the enclave. That means I cannot put any secrets in that enclave. Well, I can encrypt parts of the enclave so that I put encrypted data in there, but I somehow need to have the encryption key to be able to decrypt it inside of that enclave. And so how can I get that encryption key? If I would have that encryption key, I could have, say, encrypted code by having an encrypted library on the outside, and I start my enclave and then I later on load that encrypted library. I could also have encrypted files that I load in, with my data in, so I can later on get more secrets into my enclave via files, libraries, but still I need some secret inside my enclave to be able to decrypt that. Or in the case of the SCOAN runtime, what we do, we automatically decrypt that for the application. So the application doesn't even know that this library was encrypted or the file was encrypted. We do that transparently. You have a policy that says, okay, there's a file or file region, everything under this path that should be automatically encrypted or decrypted. So what we need somehow is a way to give such an enclave keys, some secrets to for our libraries or SCOAN library to automatically decrypt these files. And so how do we know that we can trust the code that is inside of the enclave? For that, we need something that is called attestation and secret provisioning. And that's, I still have a few minutes. I want to focus on that attestation verification, because that is one of the most important parts of confidential computing. What we want to address is this problem 5 from before. So how can we establish trust in the CPU and the code that is in the enclave? And so let me zoom into that aspect, because that, I think, is one of the most fundamental and important parts of confidential computing. So what we want to do is to make sure that when we run a service, that this service has the right code, not modified by an adversary. So because if I'm an adversary and I could change that code, I could have some code that just exposes all the secrets to the outside. I want to also make sure that this service is run in the right environment, so in a trusted execution environment, say Intel SGX enclave. And I want to make sure this is a real hardware, it's not emulation by QEMU. I want to make sure that it's up to date, the firmware, so no known vulnerabilities that have not been addressed by either the firmware update or having a new hardware that fixes that problem. I want to also make sure that all my state at rest is correct, was not modified. It's not an old version, it's a new version that is unmodified. And I might also want to make sure that I only talk to clients that are permitted to talk to me. Because maybe a service has a vulnerability. If I permit arbitrary clients, they could expose that or activate that vulnerability. And here, I want to make sure that only certain clients can talk to this service. And so how can I do that? And attestation is your friend in this context. And here I have some busy slide where I try to explain how that is done in the context of the SCOAN runtime, a little higher level kind of workflow I want to present here. And then we zoom into what the actually Intel provides you with attestation. So here's the high level from the example from before. So we have some database here on the right-hand side. That database encrypts its database. And I mentioned beforehand, we might have a configuration file where there's a key in there, and we want to encrypt that configuration file so that nobody can see the key of that embedded in that configuration file. And so how can I get the key to decrypt that configuration file? So this is a bootstrapping problem, I call it. So how can I get secrets without knowing any secrets? And so what we have in the system is what we call a configuration attestation service, CAS. So when MariaDB is started, so in Kubernetes, this could be done with a Helm chart. So it's a deployment manager where you can say Helm install MariaDB, and then it installs it on some Kubernetes node. And what is done, then MariaDB starts, and actually some runtime that is part of the MariaDB enclave or Scone runtime will attest that MariaDB before MariaDB actually can run. And to do so, this is step 4, we go to the configuration attestation service and check, oh, do you have some secrets for us? Do you have the encryption key for the file system? And then the CAS, what it does is checks, is that TLS connection that I get, this mutual TLS connection that I get here, from a MariaDB. So is the state of that enclave, the initial state, is that as expected? So for that, there is some policy that is stored in CAS. I get to the point how to get there to that policy in a sec. And then if the CAS sees, okay, that is actually MariaDB running in an enclave on a trusted CPU, then I give via that MTLS connection, I give back the key to decrypt the configuration file. And the Scone runtime will transparently decrypt that configuration file, will start MariaDB, and MariaDB will read its configuration file and knows, oh, there's my key, I can now decrypt my database. For that to all to work, the CAS needs some policy, and you can actually attest the CAS via some command line, so you can make sure that CAS itself is trusted, and then you can create some what we call sessions or policies where you say how to attest a MariaDB, what you expect for the CPUs. You can limit kind of on which CPU the MariaDB can start. You can even say kind of on not only on which CPUs, but also what the state of the database has to be. So there are multiple things you can do in the policy. But the main functionality that you need from the underlying infrastructure is attestation. So how can I actually trust, or the CAS can trust, that this MariaDB is running inside of an enclave? There, I would like to dive a little bit deeper. So now this is kind of a hand-waving top-level introduction to attestation, and now I want to go deeper unless you have some more questions. So the idea is we have some code. Say here on the left side, we might have some code, and we want to make sure that if somebody would change that code and add some copy of the of data from secret data from the inside to the outside, we want to detect that. So any modification of the code we want to detect. So in MariaDB, we want to make sure that the expected version of MariaDB runs inside of our enclave. And Intel actually provides attestation. So it provides some way to verify what code is running inside of enclave. And if you look at the top level description, what attestation does, it already could make your head spin, because there is multiple steps. So I want to verify that my application code is running in an application enclave. So I'm a challenger. I will talk to the application, say, oh, is your enclave really in the right state? The application talks to the enclave talks back. There is then some second enclave, which is called the quoting enclave, that signs a report, and that report is sent to the challenger that can verify a certain report. And one can deep dive into these attestations. So this is, well, understandable, but it is complex. And if you have to do that for each of your applications, you spend a substantial amount of time to make this work. So therefore, what our research was focusing on is how can we make that actually easier? So that means make it transparent for the user. User just specifies what he or she wants with the help of a policy, saying, okay, please expect this, that this MariaDB, verify that for me, and then give some configuration data to MariaDB, some arguments like keys, some environment variables, configuration files with keys. And so, and all that code for attestation should be gone into the SCOAN runtime, all transparent. And so therefore, the idea is that to hide all that complexity by running the whole application in the enclave, the attestation should be done transparently without the need to understand all the itsy-bitsy details that one has to do. But since it's so nice, let me focus anyhow on the different steps. So what you would typically do to do the attestation is that the SCOAN runtime starts up in an enclave, it connects to this CAS via TLS, it gets back a nonce, so one-time password or key, then it performs something that's called local attestation, which is something that's called a quoting enclave. The quoting enclave creates a report that is signed, and that report says, basically, there is an enclave that has a certain initial state. It has an initial or a random public key that is part of the signed report. And this report is then sent back to the CAS. And the CAS verifies that, checks this TLS connection. The client has given me a client certificate with a certain public key. Does this match the report that we gotten? If it does, and the report says, oh, the initial state of this enclave is this value, and is that expected according to my policy? If that is all the case, then I send over some configuration data. So that means we have to do some local attestation. We have to have some expected initial state in a policy, and then we can give some configuration data, some keys back to the runtime. And then when we have all that, the application is actually started. If the attestation fails or the initial state is wrong, then we even don't start the application. Okay. Now it gets even deeper. Now a deep dive. Just to give you a feel what you get with the attestation. So you have this enclave, you have initially data in there, you have code in there, you might have a set of threads in there that you can start, and you want to see, is my code, my data that is in there and initially in that enclave, is that what I want there to be, like the code of MariaDB. So therefore, there is something like an initial hash of the enclave. Intel calls that MR enclave. I pronounce it Mr. Enclave because it's just easier to pronounce for me. So Mr. Enclave is the hash value of this initial, or the initial state of the hash value of the initial state of the enclave. Let's put it this way. And let me run through the attestation, how that is done low level in SGX. So here on the right-hand side, enclave B is our quoting enclave that signs this report saying, okay, this is the public key of the enclave. This is the initial state. And for this quoting enclave to learn the initial state, it says, oh, hi, I'm enclave with this initial state. Who are you? And sends that to enclave A. The enclave A has also this initial state, or the Mr. Enclave. It talks to the CPU and says, oh, please create a report for enclave B. So this is the flow is part of the local attestation. The report, the CPU gives it back. When I create that report, I will also initially put my hash of my public key in there if I'm enclave or A. So there is some part of the report that I can control. I give that report back from CPU saying, okay, here's the report, it's encrypted. And then enclave A can move that report over to enclave B. It says, it talks to the CPU, say, oh, give me some key that I can verify that the report was not manipulated on the way to me. And then the CPU gives a key, and then enclave B can verify the report, and then it can check that everything is okay. The report was not manipulated, and then enclave B signs it. And that is kind of the flow of local attestation. So there's, with the help of the CPU, I can learn the initial state of the another enclave. So the Mr. Enclave, we call it. And I can learn some public key. And so that means I can establish a communication via TLS to that enclave. Because I know the public key. Nobody else knows the private key except the enclave, because that enclave randomly created a public-private key pair, and every time it starts up. And so this, nobody else should be able to know the private key for that public key. For remote attestation, this quoting enclave, you use some from Intel. Intel has a certain way to learn the signing key of the quoting enclave, and that allows us to do actually a remote attestation. So we get such a report, and we can verify with the help of Intel that this report was created by and signed by a genuine Intel CPU. We can verify that there are no known vulnerability for that CPU. It's real hardware with up-to-date firmware. It might also, depending on the attestation service that you use from Intel, it might also say there is certain vulnerability. And then you, in your application, you have to decide if you can live with that vulnerability or if you want to stop running on that hardware. Okay. This was kind of a very short deep dive into local and remote attestation. It really gives you some benefits because you learn about the code that runs in the enclave, that it runs in a genuine enclave that is up to date, runs on up-to-date hardware with no known vulnerability, hopefully. And then you provision keys there. Something that I want to zoom in for the last few minutes is the page access versus cache line access. So one thing that was really slow on Intel SGX for many years was the accessing the encrypted memory was slowed down because you had limited EPC, so cache line encrypted part of the memory. Because typically when a CPU accesses memory, it does in cache lines. So it always reads or writes a cache line. But the main memory of the enclaves are encrypted in 4 kilobyte pages. So that means there must be some way for re-encrypting from a page encrypted memory into a cache line encrypted memory. And that in the Intel architecture was the EPC, or is the EPC, enclave page cache. And there the memory is cache line encrypted. And this EPC was very limited in size. So you had only 256 megabytes max in the previous generation. So therefore you can see in some applications quite a slowdown. These days you can have encrypted memory of multiple hundreds of gigabytes, 512 gigabytes, and you do hardly see any slowdowns regarding this re-encryption from page cache to cache line encryption. So that is right now in the Ice Lake generation kind of gone. So the overheads are therefore acceptable. So sometimes you still see some overheads, say from 20%, because you need to measure the initial state. You might also have programs that are optimized for non-encrypted execution. So therefore you see sometimes some overheads. Sometimes you see also some speed ups. So we have seen in Python that sometimes Python programs get a little faster, just a tiny bit faster running inside of enclaves. I mentioned already, so this enclave page cache was really tiny. When it started, was only 64 megabytes. Therefore, you had to re-encrypt between EPC and main memory a lot, and that could slow down your computation these days. You have large encrypted memory, and so there you typically don't see any slowdowns or not much of a slowdown anymore. So that means this paging that we had in the old days is mainly gone these days with modern server CPUs. Summary of my slides here. So what I showed you is that kind of an introduction to confidential computing. In my mind, cloud native applications are really good for structuring your confidential application, because you can decide which service should be confidential and which service should be just native, and then you plug them together via REST APIs. And there you have kind of solved the problems of partitioning your application in confidential parts and non-confidential parts, because you partition them anyhow already in microservices, and then some of them run inside of enclaves. One of the important parts here is that you make sure that you attest your application, so you detect if you run on out-of-date CPUs or you would run in emulation mode, that your firmware needs to be updated, your code needs to be updated. So attestation is your friend to make sure that you enforce cyber hygiene. So you can check that you run on up-to-date CPUs, up-to-date firmware, up-to-date code. And in this way, you reduce the vulnerabilities that you might have also in your code, because you enforce that you run the newest version of your code. Okay. Next steps. So as I mentioned at the beginning of this lecture, this is part of a lecture series. So this is just a number 1 lecture. There's a more deep dive next lectures that I typically teach. You can have also a look at our exercises. So there is some hands-on exercise on sconedocs.github.io. Code is online, it's all accessible. You might, if you really want to run this, you might need access to some container images. You can sign up for that online, and then you can try out these examples. Now I'm done with my lecture. If you have any questions, I would be happy to answer any questions that you have. Anybody?
Sir, one
Can I?
question regarding attestation.
Yes, sure.
What we saw, it was like we are checking the initial position, like whether the original software is getting run or not
Yes.
as application. But do we consider the runtime attacks and runtime context related attacks as secure in this context? I
Okay.
mean to say, when application is running,
Yeah.
so it is running on the actual hardware at some remote machine. So whether the runtime information can be used to gather some information by the cloud provider or anyone sitting over there, whether that will be counted as vulnerability in this case?
Um, so, so this is a good question. So there are, first, you're right. So the application is only checked when it starts up, and then we don't check the application anymore. This is kind of startup time. Typically, in a Kubernetes environment, you might restart your services periodically. Then say, if you sometimes this is called rejuvenation. So you could make sure that your programs are restarted periodically to be reattested. And if you have stateless services, that is not a problem. Stateful service is a little bit more of a problem. So from that perspective, there are some ways of enforcing reattestation of your services by making sure they are restarted periodically. What I didn't talk about is attestation of the environment. So what we also support is that you measure in what environment your confidential services are running. So this is required, for example, in the eHealth domain. So I have to make sure that my confidential application runs only in an environment where only certain applications, native applications, are permitted to run. And there you can actually, so we have an extension where you can continuously measure what is running in the system, and you stop your application in case there is some native application or confidential application that you don't know and that you don't want to be co-located. So in a summary, there is some way of dynamically attesting the environment, and that is also done in some application domains. And additionally, you can restart your confidential application to remeasure them. If you have later on VM client of Intel TDX, there you could also measure all the application that start during in the confidential VM. But there you would also, each application you would only measure once. So there are some extensions later on for VM-based where you continuously measure, but each application really is only measured once, because it's difficult to remeasure, because say you have Java application that have just-in-time compilation. It's really difficult to know in what state my application should be. Okay, I hope that was at least somewhat useful.
Yes, sir.
Okay, any more questions from your side?
Dr. Fetzer, thank you for your interesting lecture. So I don't know much about this field, but I could follow the basic story. Thank you so much for the great lecture. So I have a general question. So recently we have a lot of neural network based workload. So yeah. I am curious. So because from my point of view, in neural net application, the separation between this application and data is not clear. So because we have to deal with gigantic, neural network weight in your system, which is sometimes gigabyte level, but I wouldn't say this is the application. They are just bunch of data. But at the same time, these are read-only data, and this is not purely data. It is somehow telling you something to do, right? So in this sense, this traditional separation between this application data and data is still applicable this kind of application. Can you comment on this?
So machine learning is actually an interesting application domain for confidential computing, both during training as well during classification, because typically during training you need lots of GPU or CPU cycles, and you might want to you want to protect the data that is used for training your model. There you can use confidential computing. So in Scone, we actually support TensorFlow running in confidential computing. So you can protect your machine learning code as well as the data that you pipe in. And then you produce a model. So your your neural network. And that you can also keep confidential because you put all that effort into creating that neural network, and you might also want to protect that with confidential computing. And then we have also another approach where you use the confidential model that you generated, and you can run the classification of data using that model using confidential computing. So, and actually this is one interesting use case that we have seen, that people want to protect the data during training, but also the model that they generated, and also the Python code that is used for the model generation. So therefore, this domain that you are sketching is something that via confidential computing, at least in what we've seen, is interesting and also in practical use.
Okay, thank you.
You're welcome. Any more questions? I think we still have a minute or two. No, then I would say thank you everybody who attended. If you have any questions, just send me email and try to answer that. Also, if you want to get access to the platform, yeah, sign up, and then we give you, or I give you access. Thank you so much.
Thank you.
Okay, then bye-bye.
Bye.